Hello everyone and welcome back to Chemistry Time. In today's discussion, we'll be focusing on how we measure work done by a system as well as using enthalpy to measure changes in energy of chemical reactions. So without further ado, let's get to work. We have talked a little about work in our previous discussions, but I want to expand on this a little bit more. Work is the transfer of energy that occurs when an object is moved over a distance that is the result of an external force. To calculate work is equal to force times distance. Another way to calculate work in the case of a reaction is calculating pressure-volume work, and work is equal to the negative pressure times change in volume, where pressure is the external constant force and the change in volume, which relates to the distance. One way we can determine pressure-volume work is if we had a cylinder with a movable piston. Let's take, for example, dissolving copper in nitric acid, which has the following chemical equation. The formation of nitrogen dioxide gas will push the piston upward, causing an increase in volume while keeping the pressure constant. We can calculate the work by multiplying negative pressure by the change in volume. The reason why pressure is negative is to indicate that when the volume increases, the system loses energy. When dealing with pressure-volume work, it is important to remember to convert the units from liter atmosphere to joules by using the following conversion factor. 1 liter atmosphere is equal to 101.3 joules. If a reaction occurs at constant volume, then no pressure-volume work can be achieved because the change in volume will be zero. In this case, the internal energy is equal to the heat. The subscript V next to Q is used to indicate that this process occurred at constant volume. An important thermodynamic quantity is enthalpy, which is used to determine the change in energy that occurs in a chemical reaction. Enthalpy is the sum of the internal energy of a system that is related to the heat transfer to and from a system plus the product of pressure and volume. Enthalpy is a state function and is dependent on other state functions, so we are only concerned about the initial and final states. Therefore, enthalpy is given by the following equation. However, we can simplify this equation. If pressure is held constant, then the change in enthalpy is equal to heat gained or lost and is denoted by a subscript P. To signify pressure is held constant, when studying energy changes for a reaction, one of the important quantities that is used is the change in enthalpy for a reaction and is denoted by a subscript Rxn. This will allow us to determine the flow of energy. For a reaction that is exothermic, heat flows from the system to the surroundings, and the enthalpy of the reaction is negative and is energetically downhill. For an endothermic reaction, enthalpy is positive and is energetically uphill. For endothermic reactions, the heat flows from the surroundings to the system. It is important to note that when bonds are broken, they always require an input of energy, whereas bond formation releases energy. Let's take, for example, ice melting, which is written as H2O solid to H2O liquid, which has an enthalpy change of positive 6.01 kilojoules per mole. In this scenario, heat is absorbed by the surroundings to facilitate this physical change and is an endothermic reaction. This differs from a combustion reaction, for example, methane, which has an enthalpy change of negative 890.4 kilojoules per mole. This is an exothermic reaction and releases energy to the surroundings. The per mole is in reference to the stoichiometric relationship that when 1 mole of CH4 reacts with 2 moles of O2, it produces 1 mole of CO2 and 2 moles of H2O. It is important to note that the change in enthalpy value is negative 890.4 kilojoules per mole is not per mole of a single species in the reaction, but refers to all the species in the equation. This can be expressed as the following. We'll be using this relationship moving forward, and it is important to familiarize yourself with this convention. There are a few guidelines to follow when dealing with thermochemical equations, which are chemical equations that include the enthalpy change. Firstly, when dealing with thermochemical equations, you must always include the states of matter for each species in the chemical equation. States of matter is pertinent for determining the change in enthalpy and can differ depending on the state of matter. Second, if a thermochemical equation is multiplied by some factor, the enthalpy change is also multiplied by the same factor. For example, if we have the thermochemical equation for water melting and we multiply it by a factor of 2, we also need to multiply the enthalpy change by 2, giving us a positive 12.02 kilojoule per mole. Third is that if a thermochemical equation is reversed, the sign associated with the enthalpy change is flipped. For example, if we reverse the equation for the melting of ice and look at water freezing, the enthalpy change for this reaction will be negative 6.01 kilojoule per mole. Let's do a practice problem together. Consider the following thermochemical equation for photosynthesis, which has an enthalpy of positive 2,803 kilojoules per mole. How much solar energy is needed to produce 75 grams of glucose, which is C6H12O6? Firstly, we need to determine the amount of moles in 75 grams of glucose, and then we can calculate the solar energy required. To determine the number of moles, we need to divide by the molar mass of glucose, which is 180.2 grams per mole, and is equal to 0.416 moles of glucose. Next, we need to multiply the entire expression by 0.416 moles, including the enthalpy change. Keep in mind the number of moles cancel, and we determine 1.17 times 10 to the third kilojoules of energy is required to produce 75 grams of glucose. I want to point out one way to check your work is that you have less than a mole of glucose, meaning that the enthalpy associated should also be less than half. Let's try one more example using the same thermochemical equation, but instead let's calculate the mass in grams of oxygen that is produced when 2.49 times 10 to the fourth kilojoules of solar energy is consumed. We need to set up a series of conversions. However, keep in mind the change in enthalpy value does not mean per mole of a specific reactant or product, but refers to all the species in a balanced thermochemical equation. Keeping this in mind, we can express the change in enthalpy as 2,803 kilojoules per 6 moles of oxygen. We are looking for the mass of oxygen and need to first determine the moles of oxygen. We set up the following conversion with moles of oxygen in our numerator and multiply by 2.49 times 10 to the fourth kilojoules. We are left with 53.3 moles of oxygen produced. To determine the mass, we multiply by the molar mass and we calculate that 1.71 times 10 to the third grams of oxygen is produced. In today's discussion, we showed how we measure work done by a system using pressure and changes in volume. We also discussed how to use enthalpy to measure changes in energy in chemical equations. Thank you and have a wonderful day. Thank you.